let's look at the uncertainty question. Now, notice that if you look at A acting on ket alpha is alpha alpha, this immediately gives us, since alpha is normalized, if you hit this with a bra alpha, for those unfamiliar with the bracket notation, this is psi alpha star operator A acting on psi alpha integrated. Simply gives you alpha because ket alpha times ket alpha, this number just comes out of the integral, and ket alpha times bra alpha acting on ket alpha is just 1. And taking the adjoint of this, we immediately get alpha A dagger alpha. This expectation value is alpha star. So operator, the raising and lowering operators both have very simple expectation values, namely alpha and the conjugate of alpha. But now, remember, we made our A and A dagger out of X and P. And we can just invert those equations to get X and P out of A and A dagger. In particular, X becomes this. And since root over H cross by twice M omega is just a numerical factor, it can come out. And you can just get the two expectation values of A and A dagger being positioned here. And therefore, this is a very simple result. Simply, X squared expectation value, well, you will need A plus A dagger whole square. Now that expands to A square plus A dagger square plus, again, as you all know, commutation is something we assume for ordinary numbers, but operators don't necessarily commute. If they don't, A and A dagger has a commutator of 1. So you cannot write A plus B whole square as A square plus B square plus twice AB, but you can write it as A square plus B square plus AB plus BA. And you end up with this, A dagger plus A dagger A. And what will make life easier for us is that you can replace the A dagger by A dagger A plus 1 from the commutation relation. So this is what you get. Now, A acting on alpha gives you alpha acting on ket alpha. Another A acting on alpha gives you alpha square. So this will just give you alpha square. Similarly, this will give you alpha star square. This one will give you alpha, this one will give you alpha star. So basically, this is what you get. Now, the reason why I've written this in red, you may have already figured that out. Look at this expectation value for X. If you square that, what you get is exactly these terms. H cross by twice M omega, alpha square plus alpha star square plus twice alpha star alpha. What you do not get is the additional plus 1. What that means is delta X squared, which is X squared expectation value minus X expectation value whole squared, is simply given by this quantity, H cross by twice M omega. Now, a very similar calculation, which you can all carry out yourself, will give you delta P square. Exactly similar, very little change except for the factors, get H cross M omega by 2. But when you multiply the two, note that the M omega cancels and you get H cross square by 4. And that's for the square of delta X times the square of delta P. And that tells you that for all coherent states, delta X times delta P is exactly H cross by 2. So coherent states give you non-trivial oscillations. These are not stationary states in general, if you leave out the ground state, which of course is a very special case. All other coherent states do show expression of X and expression of P, which oscillate really, and they satisfy this uncertainty bound H cross by 2. And well, in order to make the relation even more striking, we can define dimensionless versions of capital X and capital P. If you look at these equations, delta X and delta P look a bit different. But that's simply because they're dimensional quantities with different dimensions. Of course, they will never look the same. But if you look at dimensionless quantities like this, where you have taken out this factor, which has the dimensions of position, which is simply A plus A dagger by 2, and capital P hat, which is again a dimensionless version of small p hat, which is A minus A dagger by twice psi. These are very similar to X and P except for these factors, and you can easily check that their commutation relation is also very much like the canonical commutation relation IH cross for small x and small p, but because Because of these dimensionless factors, it has become I by 2. And the uncertainty product, which you expect for x and p, is delta x times delta p is greater than or equal to 1 by 4. This, by the way, is true for all systems, not necessarily harmonic oscillators, all one-dimensional systems. But the coherent state in particular obeys this very special result. The delta x and delta p are exactly equal and equal to half. So a coherent state not only has the minimum uncertainty product, it has the same uncertainty in the dimensionless versions of x and p.